In this video, we discuss two chi-squared tests, namely the goodness of fit test and the independence test. What is a chi-squared test? A chi-squared test is a statistical procedure for testing for evidence of a relationship between two categorical variables. Essentially, we compare observed outcomes to those outcomes expected if there is no relationship between the variables. An important caveat to remember is that these tests look for evidence a claim is false. They do not establish that a claim is true. There are two basic chi-squared tests. The goodness of fit test is used to test whether a one-variable frequency distribution fits a specific pattern. The independence test is used to test whether two categorical variables are independent. The basic procedure for conducting a chi-squared test is similar to the procedure for any significance test. First, we state our hypotheses. The null hypothesis is always that there is no difference in outcomes by category. The alternate hypothesis is always that there is a difference in outcomes by category. Because these hypotheses are always the same, it is rare to see them explicitly stated in practice. Next, we must calculate the expected data assuming the null hypothesis is true. We will show how to do this in our examples. Then we use technology to compute the p-value for the observed statistics. Compare the calculated p-value to the significance level alpha, and make our decision. If p is less than or equal to alpha, we reject the null hypothesis in favor of the alternate hypothesis. If p is greater than alpha, we fail to reject the null hypothesis. Finally, summarize the results. We will show 5 examples. The first 2 use goodness of fit tests, and the last 3 use independence test. To test whether consumers have any preference among 5 flavors of a new fruit drink, marketers conduct a survey of 100 people. If consumers have no preference among the flavors, then each flavor would have an expected outcome of 100 divided by 5, or 20 votes. This is our expected outcome. The data for the survey is given along with the expected data if no preference is shown. The question we want to answer is, does a preference exist among the consumers, or are the observed differences due to chance? To proceed, we explicitly state our hypothesis. We then put our observed data in list 1 and the expected data in list 2. Then we conduct the goodness of fit test. Under the statistics test menu, we select GOF test. GOF stands for goodness of fit. We indicate the observed data is in list 1 and the expected data is in list 2. We also have to give the degrees of freedom indicated by DF. For the goodness of fit test, this is 1 less than the number of categories from the data. We had 5 categories. They were cherry, strawberry, orange, lemon, and grape. Thus, we have 5 minus 1, or 4 degrees of freedom. When we hit calculate, the output data is displayed. We note that the p-value is 0.00123, which is less than 0.05, so we reject the null hypothesis in favor of the alternate hypothesis. Thus, there is evidence of a flavor preference among consumers. If we want to know what that preference is, we need to conduct further tests. For extra practice and to increase our familiarity with the goodness of fit test, let's consider a second example. This time we start with a question. Are births evenly distributed throughout the week? Birth day data was collected on 700 births at one hospital. If births were evenly distributed throughout the week, each day would have an expected outcome of 700 divided by 7, or 100 births. The observed data is given along with the expected data in the table. To continue our solution, we explicitly state our hypotheses, put our observed data in list 1 and the expected data in list 2, and then conduct the goodness of fit test. Again, under the Statistics Tests menu, we select Goodness of Fit Test. We indicate the observed data is in list 1 and the expected data is in list 2. This time we have 6 degrees of freedom since there are 7 days of the week. When we hit Calculate, the output data is displayed. We note that the p-value is approximately 0.00396, which is less than 0.05, so again we reject the null hypothesis in favor of the alternate hypothesis. Thus, we can conclude that not every day of the week is equally likely for births. Now let's consider examples in which we utilize the independence test. The situation is that a new post-op procedure has been implemented at a local hospital. A survey was conducted of 200 nurses and 200 doctors, asking about a preference for the new procedure versus the old one. We want to know whether doctors and nurses feel differently about the new procedure, or are any observed differences due to chance. This time we have the observed data given in the chart. There are 2 categorical variables. One is profession with values of nurse or doctor. The other variable is preference with 3 possible values. The total column indicates a total of 200 nurses and 200 doctors. The total row shows a total of 150 people prefer the new procedure, 200 prefer the old procedure, and 50 have no preference. The total number of individuals is 400. We have to calculate the expected outcomes if there is no difference of opinion by profession. In this case, since the number of nurses surveyed and the number of doctors surveyed are equal, we should have an equal number of nurses and doctors with each opinion. So the 150 who prefer the new should be evenly split into 75 doctors and 75 nurses. The 200 who prefer the old procedure would be evenly split into 100 doctors and 100 nurses. And the 50 with no preference would be evenly split into 25 doctors and 25 nurses. To compute these values in general, we multiply the row total by the column total and divide by the total total. For example, to compute the expected number of nurses preferring the new procedure, we multiply 200 row total by 150 column total and divide by 400. We continue this process to fill in each box. Now that we have our observed and expected data, we can proceed with the independence test. We explicitly state our hypotheses. For this test, we need to input our data into matrices instead of lists since the data is two-dimensional. Then we conduct the test. Notice that this time we don't have to input the number of degrees of freedom. The output indicates a very small p-value, one that is essentially 0. Therefore, we reject the null hypothesis in favor of the alternate hypothesis. We conclude that there is evidence of a difference of opinion among nurses and doctors. Let's consider another example. Again, we start with the question, does seatbelt use by drivers differ by ethnicity of the driver? Data on seatbelt use by drivers in Houston, Texas was collected. The data represents two categorical variables given on each of 1,166 drivers. One variable is driver seatbelt use with values of belted or unbelted. The other variable is driver ethnicity with possible values of Black, Hispanic, and white. In fact, this data was originally presented with only counts for belted drivers and total by race. I had to do some subtraction and rearrangement of the data to put it in this more useful form. We still have to calculate the expected outcomes under the assumption that there is no difference of seatbelt use by ethnicity. For each box, we multiply the row total by the column total and divide by the total total. In the independence test, the most difficult part is calculating these expected values. Notice that 369 times 838 divided by 1166 is 265 when we round. So the first row total times the first column total divided by the total total gives the entry in the first row and first column of the expected outcomes. Similarly, the second row total times the first column total divided by the total total gives the entry in the second row first column of the expected value matrix. Now we are ready to conduct our test. We state our hypotheses, although you could probably see why this is often omitted in practice. We input our observed data and expected data in matrix A and matrix B respectively, and then conduct the test. The output shows a p-value of about 0.1047, which is greater than 0.05. Thus, there is no evidence of a difference in seatbelt use by driver ethnicity. You've probably seen enough examples to have a general idea of how chi-square tests work. However, to illustrate the independence test with categorical variables taking on more values, let's look at one final example. We know that smoking status among American men differs by education level, but Europeans may not experience the same issue. Does smoking status among French men differ by level of education? We have observed data from 459 French men. The two categorical variables are smoking status and education level. Smoking status can be one of 4 categories, and education level can be one of 3 levels. Having more possible values for our variables just makes our matrix of data larger. We still have to calculate the expected outcomes under the assumption that there is no difference in smoking levels. For each box, we multiply the row total by the column total and divide by the total total, and the expected data is shown in the table. Now we're ready to conduct our test. We know the hypotheses, we put the data in the appropriate matrices, and conduct the test. Our p-value indicates that we reject the null hypothesis and conclude that level of education is related to